Our next topic, which will be mediation analysis with survival data. And we're not going to spend too much time on this, in part because the results are actually going to look exactly like everything else we've seen so far, and in part because this really wasn't a formal prerequisite for the course. But because these models are used very commonly, I thought it would be good to at least briefly address it. So if you're not familiar with survival analysis, don't worry too much. We'll hopefully be speeding through this material in sort of the next 20 to 25 minutes. But sort of the long and short of it is that we can do something very similar with proportional hazards models, and that looks like it did sort of with logistic regression, the same formulas, the same sorts of problems and issues. And we can do the same type of thing with accelerated failure time models, and that looks pretty similar to what we had for the log binomial model. We'll cover a couple of additional topics as well. We'll sort of start with some of the early literature on the social sciences. We'll talk about different scales on which we might do mediation analysis with time to event data. We'll talk about the proportional hazards and accelerated failure time models. Talk about an alternative that's been developed in the mediation context using additive hazard models. Talk a little bit about sort of a weighting approach to mediation analysis using proportional hazards models with a common outcome, and we'll briefly mention sensitivity analysis for mediation. But it's all going to look pretty much the same as we had before. So until a couple of years ago, the only paper on mediation with survival data was a paper by Teen and McKinnon, and they considered whether the product method and the difference method coincided for time to event models. And they found that with the accelerated failure time model, the two approaches coincided numerically, and with the proportional hazards model, they didn't. And so that's sort of where the literature was until about 2011, when this material began to develop more substantially. We'll be using the following notation throughout. For some time to event outcome V, we'll let SV be the survival function at time t. So in other words, the probability that our time to event outcome exceeds the value t, that the outcome occurred after value time t. And we can likewise define that conditional on the covariates. We'll use lambda vt, or lambda vt conditional on c, to be the hazard or conditional hazard at time t. In other words, sort of the instantaneous rate of the event conditional on survival up to time t. And we saw that with a binary outcome. For example, we could do mediation on different scales. We could do it on the difference scale. We can do it on the odds ratio scale or the risk ratio scale. And we're going to have something similar here. We can do mediation analysis with time to event data on different scales. But our definitions themselves, the counterfactuals that we're comparing, are going to be the exact same thing as we had before. Just what we're changing is the scale. So, for example, we could decompose the total effect of the exposure at time t on the survivor function scale. We could consider the time to the event when exposed, the time to event when unexposed, and we can consider the survivor functions at time t, and we could decompose that into a natural indirect effect and a natural direct effect on the survivor function difference scale. This is just the probability of survival beyond time t. How does that compare being exposed to unexposed? How much of that is indirect? How much of it's direct? But it's the same counterfactuals as before. We're asking, what's the time of the event if we were to fix the exposure to 1 and change the mediator from what it was under the absence of exposure to what it would be in the presence of the exposure? That's our natural indirect effect, same thing we had before. And likewise, our natural direct effect, we fix the mediator to what it would have been in the absence of the exposure, we change the exposure from absent to present, and we see how that changes the time to event outcome. Specifically here, the survival function at time t. But we could do the exact same thing, say, on a hazard difference scale, where we decompose the difference in hazards at time t, comparing exposed to unexposed, into a hazard difference indirect effect and a hazard difference direct effect. It's the same counterfactuals again, we've just changed the scale. Or we could look at mean survival times. What's the mean survival time? could look at the total effect for that. We can decompose that once again into a natural direct effect, natural indirect effect on the mean survival time scale. Or we could do it with quantiles. Again, with survival outcomes, we can do it on any of these different scales. We could do the hazard difference scale conditional on the covariates, or the survivor function scale difference conditional on the covariates. Or we could consider using ratio scales, effectively log difference scales. So we could decompose the log hazard at time t, comparing the exposed and the unexposed, to the difference in log hazards for the indirect effect and the direct effect. If we exponentiate, what we get is the hazard ratio at time t, the total effect, comparing the exposed and the unexposed, decomposes into a hazard ratio for the natural indirect effect and a hazard ratio for the natural direct effect. But all of this sort of carries on in a straightforward way from what we had before. It's the same counterfactual contrast, we're just changing the scales. And different scales, as we'll see, are going to correspond more naturally to different types of regression models. Just as with linear regression, that corresponded naturally to mediated effects on the difference scale, logistic regression on the odds ratio scale. So here, different types of models for time to event data will correspond to different scales. Question?
Yeah. Could you just comment on the timing of the mediator of when the modification arises? So up until now, like
yeah. We're going to get there. We're going to get there.
Even conceptually, in terms of the definitions of these things, it seems like it's not trivial.
It is. It is not. You're right. And I think we're getting there right now. Okay. So the assumptions we make are going to look very similar to what we had before. There's going to be one slight twist, which is what Sebastian was touching upon. So we're going to make the same confounding assumptions that conditional on the confounders, measured confounders we've controlled for exposure, outcome confounding, mediator outcome confounding, exposure mediator confounding, and none of the mediator outcome confounders are affected by the exposure. We take the same confounding assumptions, we replace our binary or continuous outcome y with a time to event outcome t, and we've got the exact same assumptions. What, however, we're also implicitly assuming here in all of our definitions is that the mediator is measured for everyone before the time to event outcome occurs. So if our mediator is defined as sort of BMI at 2 months follow-up, these methods and the whole of the literature on mediation for time to event outcomes, at least to date, effectively assume that the event that you're interested in will not occur before 2 months, which is when the mediator is measured. And that's because we can't really define the effect of the mediator if the mediator hasn't occurred, if the mediator is undefined because the outcome occurs before the mediator is measured. So this is a limitation of the current methods, but touching on Sebastian's question, it's not even clear how we would define direct and indirect effects if we relaxed it. What do you mean by the effect of the mediator? What do you mean by mediation if the mediator doesn't occur before the event does? I'm not saying it's not possible. I'm not saying methods couldn't be developed to get around this, to address it. What I am saying is that the existing methods, what we have currently, all assume, not just from sort of a standpoint of identification and assumptions, but even from the standpoint of defining the effects, they assume that the mediator's been measured before the outcome can occur. And so it is a substantial assumption. We talked earlier about how assumption 4 could almost be seen as an assumption that the mediator doesn't occur too long after the exposure, because if it did, if we had a long time gap, there's likely something on the pathway that also affects the outcome independently, and consequently is a mediator outcome confounder affected by the exposure. This further assumption with mediation analysis with time to event outcomes is almost like an extreme form of that assumption. We are assuming that the mediator is always measured before the outcome can occur.
Is it assumed to be measured at the same time point for
It wouldn't necessarily, that wouldn't necessarily have to be assumed. You do need these confounding assumptions to hold. It's going to be the same confounding assumptions. That could complicate things. You need to assume that the association between the mediator and the outcome actually reflects the causal effect of the mediator and the outcome. That's essentially what the confounding assumptions are getting us. So this is still an area where I think there's conceptual development that needs to be done. But beyond that twist, everything else, once we've made that assumption, which is strong, everything else pretty much is going to follow the same pattern as we saw before. But again, this is not just an issue of are we making strong enough assumptions, are we getting identification? This is what do we even mean by mediation if the mediator's undefined, if it doesn't exist before the outcome occurs? How do we talk about mediation if that's the case?
Isn't that true for your all the other components? I mean, this is not just isolated to survival.
Yeah. That's right. It sort of comes into prominence in survival because this is often the type of data where we might encounter more naturally violations of that, but we were assuming the same thing before as well, sort of implicitly in the notation we were using. Okay. So again, we'll start with proportional hazards models. The summary is this looks exactly like what we had for logistic regression. So we're going to fit a proportional hazards model. We model the hazard at time t as the baseline hazard, multiplied by e to main effects for the exposure of the mediator. We can allow for exposure-mediator interaction, include effects for the covariates. If our mediator is continuous, we could just fit a linear regression for the mediator model. Provided the outcome is rare at the end of follow-up. So this can be a strong assumption with time to event data. But provided the outcome is rare at the end of follow-up and our confounding assumptions hold, models are correctly specified, the natural direct and indirect effects on the log hazard difference scale, if we exponentiate on the hazard ratio scale, are just given by these expressions here, which take exactly the same form as what we had for logistic regression. If we replace our thetas in the logistic regression with these gammas from the proportional hazards models, these are the exact same expressions. And likewise, the expressions for a dichotomous mediator are exactly the same as what we had for logistic regression. Same standard errors as well. And like we had with logistic regression, these analytic formulas only hold if the outcome's rare at the end of follow-up. That's to get the math to work out. And that's also because the hazard ratio, like the odds ratio, is not a collapsible measure. Question?
So when you say outcome is rare, do you mean that the hazard is small? And how do you quantify that?
It's not that the hazard's small. It's at the end of follow-up, sort of not much beyond 10% of the populations had the outcome.
Still around 10%.
Yeah. But the hazard ratio, the hazard at any given time could be quite high as long as that it doesn't extend too far. Yep.
Is the power in these models directly dependent on the number of events?
It will be, yeah.
So you need pretty large sample sizes in that case if you have a rare outcome.
Yeah, you would. I mean, if it's sort of around 10%, perhaps not too bad. If you're looking at 2%, yeah, you'll need large sample sizes. Same with logistic regression. There, we could get around that partially with case control designs. Yep.
What about mediator itself as some time to event?
That's still an open question. Yep, no, that's a good one. That's I think there's someone at the School of Public Health working on that, but as far as I'm aware, no methods for that yet. We will go on to describe a method that can be used with the proportional hazards model with a common outcome using a weighting approach. We don't sort of get analytic formulae, but it's fairly easy to implement in software, so we'll describe that at the end of this lecture. But if we're just using these sorts of formulas, then we need that rare outcome assumption. In the absence of exposure-mediator interaction, this actually just reduces to the product method as before. But once again, for that to work, we need the outcome rare at the end of follow-up. Here, the product method, even if we don't have a rare outcome, will actually give us a valid test for mediation, but not a valid estimate. Will give us a valid estimate only if we have got that rare outcome assumption. And I think this isn't quite been shown yet. I'm pretty sure that the product method, the difference method, if the outcome is rare, then the product method and the difference method will approximately coincide for the proportional hazards model. So the product method will be a valid test even with a common outcome, but the difference method will not be. I think it's conservative, but haven't been able to show that yet. So again, pretty much analogous results to logistic regression. Same interpretation, same formulas, same limitations. Any questions on that? Okay, things are slightly happier with the accelerated failure time models, used somewhat less, but perhaps the second most popular class of models, where we modeled the log survival times linear function of the exposure mediator. We can include an interaction term covariates and an error term with a scale parameter. So for example, if the error term follows extreme value distribution, t would be y-able, but you can use these approaches more generally. Once again, if the mediator is continuous, we could fit a linear regression. If it's binary, we could fit a logistic regression. Provided the models are correctly specified, we don't need a rare outcome assumption here. Provided the models are correctly specified and our confounding assumptions hold, we can combine the estimates to obtain natural indirect effects and natural direct effects on the log difference expected survival time scale. If we exponentiate on the expected survival time ratio scale, and the formula, again, is the same as we saw for log binomial regression. And like log binomial regression, we don't need the rare outcome assumption. Same formulas as well. If we have a binary mediator, same formulas for the standard errors. So everything essentially goes through. In the absence of interaction, the method we're describing here reduces to the product method, and that coincides numerically with the difference method. So everything sort of works out pretty well with the accelerated failure time models. Any questions about that? Yep.
A slightly different question is that, are you treating sensitive data the same way? You also sensitive the mediator if the output is sensitive?
Yeah, so it's treating so the methods will be assuming non-informative censoring throughout, and so the time to event outcome model will be fit using the censoring, but it will fit, the SAS software will fit the mediator regression for everyone. Yeah. Other questions? Again, both the proportional hazards model and the accelerated failure time model have been implemented in the SAS macro. They've not been translated yet to the SPSS or Stata macros. Okay. So one of the other earlier papers in the causal inference mediation analysis literature for time to event outcomes was a paper by Long and Hansen using additive hazard models for time to event outcomes. These aren't so popular in the US, but much more popular in Europe, especially the Scandinavian countries. And I think in this context can be quite a useful approach, where we model the hazard as a linear function of a baseline hazard, which will eventually allow it to depend on time, main effects for the exposure mediator, and covariates. We could once again, for for a continuous outcome, we could fit a linear regression model for the mediator. And Long and Hansen show, and it's quite an involved proof, but they show that if the models are correctly specified, we can combine the estimates to get natural direct and indirect effects that essentially just correspond to the product method. The indirect effects, beta 1 times theta 2, effect of the exposure on the mediator times the effect of the mediator on the outcome on the now hazard difference scale, and the direct effects just lambda 1, our coefficient for the exposure in the model that includes the mediator. And they generalize this additive hazard approach in a number of different ways. Their method and their software as well can allow all of the coefficients to vary over time, and you get the same sort of straightforward product method type expressions. They also allow for exposure-mediator interaction. They don't get closed-form solutions in this case, but their software can still estimate the direct and indirect effects. And they also generalize it yet further to sort of multiple event types. So it's a pretty, I think, useful software package and way to go about mediation analysis in this time-to-event outcome context. And actually, most of the applications of mediation for time-to-event outcomes have used this package to date. And until recently, it really was, I think, the only easily usable package available. Any questions on that? Okay, we're going to keep moving at a fairly rapid pace. We'll now discuss sensitivity analysis for time-to-event outcomes. And basically here, the techniques are going to look exactly like the techniques we looked at for the ratio scale. The hazard ratio scale is going to correspond to the risk ratio scale. The only thing we're going to change is our definition of gamma. Before, on the ratio scale, we defined gamma as the risk ratio for the effect of U on the outcome, not through the mediator. And we're going to switch that risk ratio to a hazard ratio. But other than that, the formula looks exactly the same. The prevalences we have to specify are exactly the same. How we get corrected estimates and confidence intervals are exactly the same. We just divide the estimate and both limits of the confidence interval by the bias factor. The one complication is that this approach works now, provided the outcome is rare. So that's unfortunate, but for these easy-to-use formulas to hold, we need to make that assumption once again. So it restricts the applicability somewhat of these methods. And we can likewise do this on the hazard difference scale. And that method for sensitivity analysis is going to correspond exactly to our sensitivity analysis method for controlled direct effects. On the risk difference scale, the one exception is we're on the risk difference scale, our gamma parameter, the effect of U on the outcome, was defined as the difference in the risks of the outcome, comparing those with versus without U. Conditional on M. Now we're going to replace that risk difference with a hazard difference. But otherwise, everything goes through exactly the same parameter for the prevalence difference of U, same formula for the bias factor, and to get corrected estimates, we just subtract our bias factor from the estimate and both limits of the confidence interval. Once again, however, even on the hazard difference scale, the sensitivity analysis approach only applies if the outcome's relatively rare at the end of follow-up. These methods are for controlled direct effects in the absence of exposure-mediator interaction. They could be used as well for natural direct and indirect effects. So that's all we're going to talk about with regard to sensitivity analysis for mediation for time-to-event outcomes. Again, the results are essentially just analogous. All we do is we replace our risk ratios or differences with hazard ratios or differences for our gamma parameter. Okay, There's been some other work on mediation analysis with time to event data. One paper proposes what's called multiply robust estimates, where we fit a model for the mediator, a model for the outcome, and a model for the exposure. And provided two of those three models are correctly specified, we get correct estimates, so we can get around issues of model specification a little bit. Another paper looks at estimating controlled direct effects with survival data when we have a violation of assumption 4, when there's a mediator outcome confounder affected by the exposure. That will in fact be the topic of our next and final set of lecture slides. But that's been done in the time to event context as well, but software still needs to be developed for the implementation of these methods. The one other approach we will discuss in a little bit more detail here is a 2012 paper which looked at weighting approaches for proportional hazards models with common outcomes. And because proportional hazards models are used so frequently, and because outcomes often not rare at the end of follow-up, I thought it was important at least to go through this one additional case. And essentially what we do is we're going to control for confounding not by regression adjustment, but by weighting. And using that weighting approach is going to allow us to essentially get around that problem of needing to assume a rare outcome by the end of follow-up. And the analytic approach is as follows. We're going to essentially just fit a proportional hazards model to our data, but with two modifications. The first is that we're going to weight our observations using some weights described below. And the second is that we're actually going to modify the data set so that there are two copies of each individual, and we're going to sort of add another variable in. So we'll describe how we actually do this in practice. We'll go through the description of how to do this using a binary exposure. The approach can be extended to categorical or continuous exposures. It's a little more complicated, but they do provide code for these different settings. Okay, so first we'll describe how we modify the data set, and then we'll talk about the weights that we use in the final regression. So we're going to create a new data set where we create two copies of each individual. And we're going to create an additional variable, call it A star. And we're going to set A star to A, to the actual exposure, for the first copy of the individual. So for the first copy of each person, our new variable A star is just the same as their actual exposure level. And for the second copy, we set A star equal to the opposite, 1 minus A, the opposite exposure, sort of corresponding to what would happen had they had the exposure that they didn't receive. Okay. We're then going to use a weighting approach to control for confounding. And this is sort of going to look like propensity score adjustment, or weighting by a propensity score. And so we're going to do two different weights, one for the exposure, one for the mediator, sort of like a propensity score for the exposure, a propensity score-like measure for the mediator. For the exposure, we're going to estimate, we can do that with logistic regression, the probability that an individual had the exposure that they actually had conditional on their observed covariates. So we could just fit a logistic regression model of the exposure on the covariates, and then we get the predicted probability of their having the exposure that they actually had. So the predicted probability itself of having the exposure for those who are actually exposed, and 1 minus that predicted probability for those who are actually unexposed. Because for the unexposed people, we want the probability for that individual of being unexposed conditional on their covariates. So 1 minus the probability of being exposed. In the numerator, we just have the overall probability of having the exposure they actually had. That's our weight for the exposure. Our weight for the mediator, we do something similar. We get the probability of the individual having the mediator value they actually had, conditional on their actual exposure and their actual covariates. That's our probability for the denominator. Our probability for the numerator is the predicted probability of their having the mediator value that they actually had, conditional on their value of A star, that's again A for the first copy of the individual, 1 minus A for the second copy of the individual, and their actual covariates. So once again, we could just fit a logistic regression model for the mediator, conditional on the exposure and the covariates, and then we can get these predicted probabilities. The paper gives code to do all of this. Our overall weight is just the product of these two weights. And essentially what these weights allow us to do is to adjust for confounding using weighting rather than regression. So we've modified the data set, we've calculated these weights, and then to get our natural direct and indirect effect estimates, all we do is we fit a proportional hazards model of our outcome on A and A star as covariates. We don't include other covariates in the model. We're going to take care of control for confounding by the other covariates by weighting. So we just regress our outcome using proportional hazards models on our actual exposure A and sort of our modified variable A star. Those are the only two covariates in the model, but we weight this regression by that overall weight that we calculated here. One can show then that provided our 4 assumptions about confounding are satisfied, and the models for our predicted probabilities to get the weights are correctly specified, the coefficient K1 for the exposure just corresponds to the natural direct effect. The coefficient K2 for our modified variable A star just corresponds to the natural indirect effect. So it's a bit of a convoluted process, but then at the end, the estimates themselves give us our direct and indirect effects. Contrary to what's claimed in the 2012 paper, someone else noticed this, the standard errors need to be obtained by bootstrapping for these effects. They say that robust standard errors will be valid here. That turns out not to be the case. You need to use bootstrapping to get standard errors here. And I think they've published an erratum for this point. So again, a little different here than what we've looked at before. But for proportional hazards models with a common outcome, I think this is the best we have at present. We could use this approach with a rare outcome as well. That's fine. It tends to be less efficient than the regression-based approach. Questions?
This kind of approach apply with different types of outcomes, not just the time to event outcomes?
Yeah.
It's just not as efficient to use this as the other.
Yeah, so you can apply this approach with different types of outcomes. You don't need time to event outcomes here. Wouldn't particularly recommend it in other settings just because you do lose efficiency by controlling for confounding via weighting rather than regression.
Can you give some intuition behind that, those 2-3 equations that we showed you?
Yeah, why don't we wait to the 5th set of lecture notes? We'll go through another weighting approach, and then I'll try to provide some intuition there.
Do you see data code being forthcoming for this application? I mean, I know there's SAS code.
All it would take is someone to write it. Again, it's not terribly tricky. It's using status predicted command. It'd have to be a little bit careful, but it would only involve 15, 20 lines of code. Yeah. With the bootstrapping, a little bit more involved, but nothing too terrible. Other questions? Yes.
How would the efficiency of the inverse odd ratio weighting that we have published 2 weeks ago?
Yeah, so to the best of my knowledge, all of the weighting approaches are less efficient than the regression-based approaches. Another alternative is sort of to use both simultaneously with these multiple robust estimators, and then sometimes you can use the weighting approach, but also make use of the efficiency from the regression-based approaches. If you're interested in that, talking to Eric Chekin at the School of Public Health would be the best way forward. Yep.
Mediator doesn't change when your baseline values, so your exposure changes
Yeah, so there are methods either available or being developed for those sorts of settings. We won't be covering them in this course, but I can provide references.
So they are less efficient, but they are robust to misspecifications and more specifications.
The weighting approach is robust to specification of the, if you saturate this model and include an interaction, it's robust to misspecification of the outcome model, but you still have to specify models for the exposure and the mediator. And those need to be correctly specified, or at least give consistent predicted probabilities for these approaches to be valid. So you trade off one set of model specification issues for another. Final questions? Okay, so the big summary here is pretty much all the same concepts extend to time to event outcomes. The one twist in definitions where we did need to require that the mediator was measured before the outcome could occur. Otherwise, same sorts of definitions, same counterfactual contrasts, same confounding assumptions, same formulae, same restriction to rare outcome, at least in the proportional hazards setting as we had with logistic regression, same sensitivity analysis techniques, though we also had to restrict to rare outcome at the end of follow-up there as well. But some additional developments as well. We have this additive hazard approach to dealing with time to event outcomes and mediation analysis in that context. And there's also this weighting approach that can be used to address the proportional hazards model with time to event outcomes, which are common at the end of follow-up. That same weighting approach could be used in the context of logistic regression as well with a common outcome. The outcome's rare, though, generally better to rely on the regression-based approaches because efficiency is higher. Any questions on this before we move on? Okay, so our last and final topic, multiple mediators. I think we won't quite have time to cover it all, but I think we'll get most of the way through. And with the multiple mediator settings, we really are going to distinguish between two distinct sets of analyses. One set will be, we now have multiple mediators and we're interested in the effect mediated through all of them together. And that's actually going to be very straightforward. Pretty simple extensions of ideas we've already seen. That's one setting. The second setting is we have multiple mediators, but we only want to do mediation with respect to one of them, and that one we're interested in is downstream from some of the other mediators. And that's going to be the tough setting. That's the setting where prior mediators essentially serve as mediator outcome confounders, and they're also affected by the exposure. And that's the setting that's going to be a bit more challenging. We're going to need some new assumptions, some new methods, and even then, we're only going to be able to make somewhat limited progress. But the setting of how much is mediated through a whole set of mediators turns out to be a pretty simple extension of the ideas we've already seen. So we'll start with the easy setting of multiple mediators, mediation analysis through all of them. We'll then move to sort of settings with just a single mediator in the presence of multiple mediators, which introduce confounding. We'll talk about a couple of different methods to do this for controlled direct effects, marginal structural models and structural nested models. And then we'll move on to talk about what can we really do in terms of effect decomposition in that setting, where we've got a single mediator, prior mediators on the pathway so that we have mediator outcome confounders affected by the exposure. How can we try to reason about effect decomposition in those settings? So that's our plan. But the simpler settings when we just have multiple mediators, and we're interested in the effect mediated through all of them. What's sometimes done in the literature is we do mediation one at a time for each of them, and then maybe sort of sum up the proportion mediated. But this is potentially problematic. It's problematic first because with regard to that second mediator, if the mediators affect each other, that second mediator, if we did it one at a time, that's going to violate our fourth assumption because we've got M1, which affects our mediator of interest, M2, and the outcome, and is itself affected by the exposure. So we're going to run into problems if the mediators affect one another and we do them one at a time and just add up the effects. The approach is also problematic if the mediators affect one another because we're sort of double counting paths. If we had looked at the effect mediated through M1 and then the effect mediated through M2, the path A, M1, M2Y would be counted in both of those, so we'd be double counting. So that can be problematic too. And even if the mediators don't affect one another, the approach of doing the mediators one at a time and then adding them up can be problematic because we can end up actually with proportion mediateds far beyond 100%, even if all of the effects are in the same direction. So there's no sort of countervailing pathways. And that's the case that can arise if there are mediator-mediator interactions in the effects of on the outcome. And it's sort of analogous to the fact that in the presence of interactions, if we're looking at the proportion of the effect attributable to different exposures, in the presence of interactions, the proportion attributable to each of the exposures, if we sum them all up, those can far exceed 100%. Because in the presence of interactions, all it takes is removal of one exposure to eliminate that whole interaction. So if we do them one at a time, we end up getting attributable proportions that sum to much larger than 100%. Same thing can happen with the proportion mediated if we do the mediators one at a time. But instead, we can consider an approach which sort of tries to take all of the mediators together jointly at the same time. And our methods are going to look pretty similar to what we had before as our confounding assumptions. But our confounding assumptions are now going to apply to the whole vector of mediators that we're interested in, not just one. So we're going to suppose we have a number of mediators that we're interested in, M1 through Mk, and we'll denote the whole vector, M1 through Mk, by M. We're going to use the same confounding assumptions as before, but they're going to have to hold for the whole vector of mediators M. So we're going to assume that there's no conditional unmeasured covariate C, no unmeasured exposure outcome confounding. That assumption doesn't really change in the presence of multiple mediators. No unmeasured mediator outcome confounding, given our measured covariates. That now has to hold with respect to all of the mediators together. So that's going to be a bit of a stronger assumption because we're making that for every mediator. No unmeasured exposure mediator confounders, given our measured covariate C. That likewise is going to be a somewhat stronger assumption because we have to assume that that holds for the whole vector of mediators. And finally, that there's no mediator outcome confounder affected by the exposure. We're essentially making that fourth assumption again, but in some sense it's a weaker assumption here because if it's violated, we could take whatever variable is violating it, put it in our mediator vector, and take care of that assumption once again. So in some sense, assumptions 2 and 3 are a bit stronger than what we had before because they need to apply to the whole mediator vector, but assumption 4 is a bit weaker, but only in the sense that the variable that might be violating the assumption, a mediator outcome confounder affected by the exposure, is itself another mediator. We could just place that variable in our vector, mediator vector M, and that assumption would be taken care of once again. That changes the question of interest because now we're looking at a different vector of mediators. But if we're willing to do that, we can essentially get around this fourth assumption. Any questions about this? Again, the form of the assumption is very similar to what we had before. What this does allow for, what does not violate the assumptions, are a common cause of just 2 or more mediators. If we have an unmeasured variable that affects multiple mediators, but doesn't affect the exposure, and doesn't affect the outcome except through the mediators, that's not going to violate any of these assumptions. The way to think about this is if we're treating our mediator as the whole vector of mediators, then really all U is an arrow into our mediator vector. It doesn't affect the exposure, doesn't affect the outcome. It's not a confounder in this case. Okay, so what can we do analytically? What we can do analytically is fit a model for the outcome conditional on the exposure and all of the mediators together. So in our outcome model, we're putting all the mediators into the same outcome model. We're getting coefficients for the effects of all of the mediators. But in our mediator model, we're just going to do those one at a time. And one can show that provided our 4 confounding assumptions hold and the models are correctly specified, the controlled direct effect, the natural direct effect, and the natural indirect effect are just given by these expressions here, which have a fairly intuitive form. The direct effects are just essentially theta 1, the coefficient for the exposure in the model that has all of the mediators. And our indirect effect is essentially just the sum of different product method terms. But again, this is now using the product method with a single outcome regression where all the mediators are present together, rather than fitting a different outcome model for each mediator. And essentially doing this effectively prevents double counting of the paths, and in fact allows the mediators to affect one another. The mediators affecting one another does not constitute violation of any of these assumptions, and this regression-based approach is still applicable in that setting. You, in fact, don't really even have to know the ordering of the mediators to apply this regression-based approach. Standard errors can be obtained by the delta method or by bootstrapping. Likewise, we can modify this to allow for exposure-mediator interactions or to allow for binary mediators. If we added an exposure-mediator interaction between the exposure and the ith mediator, we add a theta 3i mi to the controlled direct effect, this expression here to the natural direct effect, and a theta 3i beta 1i to the natural indirect effect. And these expressions essentially correspond to what we had for our exposure-mediator interactions before. This is what happens if we added one exposure-mediator interaction, but we could add multiple ones, and we just add these terms again for the jth mediator if we did it as well for mediator j. Similar principles apply if one or more of our mediators are binary and we fit a logistic regression. We can likewise get fairly straightforward analytic expressions. Where this approach becomes more complicated is if there are either mediator-mediator interactions or if the outcome's binary. It's not impossible to get analytic expressions, but you start having to specify the covariance structure of the entire mediator vector. You begin to rely on much stronger modeling assumptions. And so what we're going to do instead, in the case of binary outcomes or mediator-mediator interactions, is we're going to use another weighting approach, which is going to make things quite a bit easier for us. Before we turn to that, any questions on the regression-based approach? Again, it's pretty similar to what we saw before. Really, the only variation is that our outcome regression, we put all the mediators in at the same time. Otherwise, the formulas look very much the same. Okay, so with a binary outcome, or if we want to allow for mediator-mediator interactions, we can proceed as follows. To obtain the natural direct and indirect effects, we essentially need 3 counterfactuals. What would happen to the outcome if everyone were unexposed? What would happen to the outcome if everyone were exposed? And the tricky one, what would happen to the outcome if we set the exposure to present but set the mediator vector to what it would have been in the absence of exposure? But once we get these 3, we can compare these 2 to get the natural direct effect, and we can compare these 2 to get the natural indirect effect. So all we need to do is obtain these 3. To obtain the first, or the second one here, what would happen if everyone were unexposed? We can use essentially a propensity score weighting approach, where we weight each subject by the weight given here. In the denominator, we have the predicted probability that the individual was unexposed, conditional on their covariates. In the numerator, the overall probability that an individual is unexposed. So we could fit this with logistic regression. And all we have to do to get this counterfactual outcome for what would happen if everyone was unexposed, we take a weighted mean of the observed outcomes for the unexposed people. So we look at all the unexposed people, we look at their outcomes, we take a weighted average of those individuals with the weights given by this expression here. What that does is essentially it uses the unexposed individuals' outcomes to predict what would happen if everyone had been unexposed. Likewise, to get the counterfactual outcome if everyone were exposed, we could take the subjects who are actually exposed, take a weighted mean of their actual observed outcomes, where we weight each of the exposed subjects by this expression here. The numerator here is the probability of actually being exposed given an individual's covariates. Again, we could obtain that just using the predicted probabilities from a logistic regression. And this is sort of a pretty standard weighting technique in the literature, essentially an inverse probability of treatment weight. The tricky one is what happens, what's the expected outcome if we were to give the exposure but set the mediator to what it would have been in the absence of the exposure. To get that, we can proceed as follows. We fit a regression model for the outcome on the exposure, mediator, and covariates, and we can make this as complicated as we want. We can add exposure-mediator interactions, we can add mediator-mediator interactions, mediator-covariate interactions, so on and so forth. Specify whatever model we want. Then for each subject, for each unexposed subject, we're going to get their predicted outcome using that regression model if we've put their mediator value to the actual mediator they had and set their covariates to the actual covariates they had, but set the exposure to present versus absent. So for each unexposed individual, we ask what would we guess their outcome would be if they had their actual mediator value, but we set the exposure to 1. In some sense, we're trying to predict what would happen if we gave them the exposure, but we left their mediator to what it would have been in the absence of the exposure. That's essentially what we're trying to get out of that prediction here. To project that to the entire population, what we're going to do is we're going to take a weighted average of those predicted values for the unexposed people, what would happen if we had given them the exposure but left their mediator unchanged, take a weighted average of those individuals where we use the weight given here, where again in the denominator we just have the predicted probability of not being exposed, of being unexposed, conditional on the covariates. So this last step's a little involved, but not too bad. Code is given in the corresponding paper and also in the book to implement this. But once we have those 3 counterfactual outcomes, we can obtain natural direct and indirect effects on the difference scale by just contrasting these 2 for the natural indirect effect and these 2 for the natural direct effect, or we could do this on the ratio scale as well by taking ratios. Standard errors could be obtained by bootstrapping. And so again, what this is going to allow us to do is proceed to do this with multiple mediators, even if our outcome's binary or some other form, even if we have fairly complicated models here, and even allowing for mediator-mediator interaction. This won't be as efficient as the regression-based approach, but with binary outcomes or mediator-mediator interactions, it's much more straightforward to do the analysis. Any questions on this? There was another weighting approach proposed in the literature for handling multiple mediators, which was pretty similar to the weighting approach we described for the proportional hazards model. But in the context of multiple mediators, it makes the additional assumption that the mediators don't affect one another, which is going to be a strong assumption. So whereas I would recommend that weighting approach of Lange, in the case of the proportional hazards model with a single mediator, in the context of multiple mediators, it's making the assumption that the mediators don't affect one another, and we don't need to make that assumption. With the method we just described, the mediators are allowed to affect one another. So I wouldn't recommend the longer weighting approach here for multiple mediators, but I would in the context of time to event data with a single mediator. There was a question, I think?
Yes, back on the previous slide, it's not clear to me whether individuals who actually have intervention are included in this expectation. Because it would appear they don't have a rate.
In this third step, yeah, we're just using the individuals who were in fact unexposed. We're using the exposed individuals to get the YAMA, but to get the YAMA star, we're just using the unexposed individuals. We're in some sense, we're using the exposed individuals as well and fitting that initial regression model in step 1, but we're not using them in the overall mean. Other questions? Okay, on we go, and unfortunately we are running out of time, but I'll try to briefly cover some of the basic ideas for this setting where we have multiple mediators, but we're only interested in one of them. But that one mediator we're interested in is causally downstream from another mediator. In other words, we have a mediator outcome confounder that is itself affected by the exposure. This setting is sometimes referred to as one of time-dependent confounding because the confounder L, which affects both the mediator and the outcome, is temporally after the exposure. So these issues arise not just in the context of mediation analysis, but also arise in the context of time-varying exposures also. But the issues are pretty similar within the context of mediation. And it turns out we're going to be able to estimate the controlled direct effects here. But we're not going to be able to simply use regression methods. And to see why that's the case, let's suppose we wanted the controlled direct effect of the exposure on the outcome, not through the mediator. Essentially this pathway from A to Y directly, and this pathway A, L, Y, the effect of the exposure on the outcome, not through the mediator. If we tried to get the controlled direct effect directly via regression, we have to decide whether or not to include that variable L in the regression or not. If we put L in the regression to control for mediator outcome confounding, that's going to be problematic because that's potentially going to block some of the effect from A to Y, not through M. So that's not going to work. But if we leave L out of that regression, we're going to still be left with mediator outcome confounding. So neither approach will work. We're essentially damned if we do or damned if we don't. Neither the regression with L or without L is going to suffice. But we can use some alternative methods, which we'll describe, to carry out this analysis where we're trying to estimate controlled direct effects in the context of time-dependent confounding. Without time-dependent confounding for controlled direct effects, we made two assumptions: that conditional unmeasured covariance C, there's no unmeasured exposure outcome confounding, no unmeasured mediator outcome confounding. The complication here is that we sort of want to control for L for the effects of our mediator, but we don't want to control for L for the effects of the exposure. So what we're going to try to do is separate these two confounding pieces. We're going to separate our confounding covariates conceptually, and we're also going to separate them in sort of our approach to analytic adjustment. So our assumptions for controlled direct effects in the context of time-dependent confounding are as follows. As before, we're going to assume that conditional on our measured baseline covariance C, there's no unmeasured exposure outcome confounding. And now we're going to assume that conditional on measured baseline covariance C, our exposure A, and our intermediate confounder L, there's no intermediate outcome confounding. So we're taking L into account for confounding for the mediator, but not for the exposure, essentially. Those are our assumptions. How do we do this analytically? One approach is to use what are sometimes called marginal structural models. These models were developed for time-varying exposures outside of the context of mediation, but they can essentially be adapted in a very easy manner to allow for controlled direct effects in the presence of time-varying confounding by essentially treating the mediator almost as a second exposure. A marginal structural model is a model for the counterfactual outcome, YAM. So we model that directly in terms of main effects for the exposure mediator. We can allow for exposure-mediator interaction. If we could fit this model, and we really can't directly because we don't know the counterfactuals for everyone in the population, but if we could fit the model, then our controlled direct effect is just beta 1 plus beta 3m. So the challenge comes in fitting this model. The model's called structural because it's a model for the counterfactual outcomes rather than the observed outcomes, which is going to make it more difficult to fit. That's why it's called structural. It's called marginal because it's for the population, the average value of the counterfactual for the whole population, rather than a conditional regression model, which is conditional on the covariance. So that's why it's called a marginal structural model. It's just a model for the counterfactual outcomes for the population. So how can we fit it? Well, we can only fit it, the only way we can really make progress is by utilizing our confounding assumptions. There's no magic going on here. It's those confounding assumptions which allow us to fit this model. So if we're willing to assume that the effect of the exposure on the outcome is unconfounded, conditional on our covariates, and the effect of the mediator on the outcome is unconfounded, conditional on our covariates, exposure, and our intermediate confounder, L, we can proceed as follows. We can once again use a weighting approach. We have an exposure weight and a mediator weight. The exposure weights, what we've seen before, the predicted probability of the exposure taking the value it in fact did, given an individual's covariates. That's in the denominator. Numerator is just the overall probability of the exposure taking the value it in fact did for that individual. And likewise for the mediator weight in the denominator is going to be the predicted probability of the mediator taking the value it in fact did, conditional on the individual's exposure, covariates, and intermediate confounder that the individual actually had. In the numerator, we have just the predicted probability of the mediator taking the value it actually did, conditional on an individual's actual exposure. So we can get these predicted probabilities by essentially just running a series of 4 logistic regressions. What we do then to fit the marginal structural model is we regress the outcome on the exposure, the mediator, the exposure-mediator interaction. No covariates. We take care of the covariates. We take care of confounding by weighting. We weight each individual in this regression of the outcome on the exposure, mediator, and interaction. We weight each individual by the product of these 2 weights. And provided our confounding assumptions are correctly specified, we get consistent estimates of the parameters of the marginal structural model, and that allows us to get the controlled direct effects. Why this approach works is essentially we separate the task of confounding for the exposure and the mediator. We can, by using weighting rather than a regression which tries to take care of all of the confounding at once, by using weighting, we can control for different variables for confounding for the exposure, where we don't control for L, and for the mediator, where we do control for L. And so that weighting approach essentially separates the confounding task so that we can control for L just when we're thinking about the effects of the mediator. That's sort of the intuition as to why this is effective. It's really just sort of 2 pages of SAS code or 2 pages of Stata code to fit this. All one really does is fit logistic regressions for each of these probabilities. You get the predicted probabilities, you form the weights, you multiply the weights together, and then you just fit one final linear regression model where you weight each subject by the weights you calculated. You need to use robust standard errors for the standard errors to be valid here. But this can be done in a pretty straightforward way with data. Again, no macros here, but it's pretty easy to adapt the code. This can be done on different scales as well. Okay, quick question, and then I'm going to move towards our wrapping up stage.
Could you use just your mediator weights
and then adjust for your baseline confounding in the model?
Yeah, that would work as well.
Is there any efficiency?
My guess is that that would in fact be a more efficient approach. You're getting slightly different effect estimates. You're getting effects conditional on the covariates rather than marginal effects for the population. So you're changing the effects, but I think that would probably be more efficient. Okay, so we're just about out of time, so I'm going to give sort of a very high-level summary of the remainder of the material. So this weighting approach or marginal structural model approach to getting the controlled direct effect is useful if the exposure and the mediator are binary or categorical. It doesn't perform so well if one of them are continuous because you have to model the whole distribution of the exposure, the mediator then. An alternative approach employs what are sometimes called structural nested models. It's actually also fairly straightforward to implement with data using sort of a two-stage regression approach. Code is given for this in a paper by Steen van Steelant, 2009 paper by Steen van Steelant. So this is also pretty easy to implement. Code is available, and this performs much better if the exposure and mediator are continuous. So those are two sets of methods that can be used for controlled direct effects when we have this problem of time-dependent confounding. Included in the notes, which you can read on your own, is an example of using the marginal structural model approach to address that question we brought up at the beginning of the course on is there a direct effect of childhood adverse SES on subsequent adult health, not through adult SES. And those analyses seem to suggest that, yes, there was, in fact, a direct effect. Sometimes using the traditional approaches here, you get fairly paradoxical results. And that, again, might be because we have this problem of intermediate confounding, where with regard to adult risk factors, our intermediate confounder here, the results, both with adjustment and without adjustment for those within a standard regression framework, would be biased. So you can read that on your own. The final topic for this fifth set of lecture notes, which we haven't been able to cover entirely, is sort of what about mediation? Okay, we can get the controlled direct effects, but what if we want to know really how much of the effects through this pathway, how much of the effects through other pathways? What if we want to do effect decomposition? And it turns out, in this context of intermediate confounding, the natural direct and indirect effects simply are not identified, regardless of whether we have data on L or not. The natural direct and indirect effects, again, were this strange counterfactual contrast where we fix the exposure to 1 to present, and we fix the mediator to what it would have been in the absence of exposure. And we need very specific data structures to be able to estimate that population. So what can we do? There are a couple of ways forward which try to get around the problem, not address directly, but sort of get around the problem. One is to rely on sensitivity analysis. We can't point identify the natural direct and indirect effects, but perhaps we can get a plausible range using sensitivity analysis. And that's sort of one set of approaches, and there are a few different techniques available to do this. Another approach is to slightly change the definition of the effects. With the natural direct effect, for example, we change the exposure from 0 to 1, and we fix the mediator for each individual to the level it would have been in the absence of the exposure. We could change that definition just slightly and define our direct effect as changing the exposure from 0 to 1 and then fixing the mediator to sort of a random draw from the distribution of the mediator amongst the unexposed, effectively just equalizing the distributions of the mediator in the exposed and the unexposed. So we're not fixing the mediator to the level it would have been for that individual had they been unexposed, but we're saying we look at the distribution of the mediator amongst the unexposed, and for an exposed person, we randomly select a value of the mediator from the unexposed distribution and set it to that. So it changes the definition of the effect slightly, but once we do that, we can actually proceed with doing effect decomposition for the direct and indirect effects, and we can do this in cases where the exposures and the mediators vary over time as well. It's a bit of a sleight of hand because we've changed our definitions, but at least in some contexts, this might actually be the effect of interest. If you think about trying to interpret the natural direct effect in the context of, say, health disparities research, if you were to ask the question, for example, what would this black person's health outcome have been if they had an SES that they would have had they been white? We're thinking about interventions on race. That doesn't seem to make too much sense. But if we think about equalizing the SES distributions between the black and the white populations, that seems to be a more sensible contrast. So at least in some settings, these alternative, slightly different definitions perhaps make more sense. When there's no intermediate confounding, everything collapses. It's all the same effects, but with intermediate confounding, they do slightly diverge. But this is another way to try to make progress. Finally, although we can't get the natural direct and indirect effects themselves, we can sort of get some path-specific effects. We can't estimate the effect of A on Y, not through M or L. We can estimate the path AMY, and we can estimate the combination of the paths AL, MY, and ALY. What we can't do is separate those last two pieces, and that's what creates the difficulty for the natural direct and indirect effects with respect to M. But we can get some of these path-specific effects. We might also ask, though, do we really care? Do we really care if we can't get the natural direct and indirect effects? We talked about at the beginning of the course that really for policy purposes, it's the controlled direct effect that's relevant. It's the controlled direct effect that asks the question, how much of the effect of the exposure would be left over if we intervened on the mediator? Often the motivation for doing a mediation analysis is said to be, well, if we find an important mediator, then we can try to intervene on it to block the path. But if that's the case, then what's interest is really not the natural direct and indirect effects, but the controlled direct effect. And the controlled direct effect we can still do even in this more complicated setting. So at least the most policy relevant questions we can tackle here. So in summary, with multiple mediators, if we're just looking at the effect mediated through a whole set of mediators, that really corresponds and very naturally to what we've done already. It extends very naturally from our prior methods. With a single mediator, with time-dependent confounding, prior mediators, which also serve as confounders, it's more difficult. Natural direct and indirect effects are not identified in that setting, but we can make some progress with sensitivity analysis techniques, with sort of doing randomized interventional analogs of our direct and indirect effects, or looking at path-specific effects. But in many cases, returning to what we discussed at the beginning, in many cases, it's really the controlled direct effect that's of policy interest, and that we can do here. I know it's been a long day. We've covered a lot of material. I've tried to structure the notes in such a way that you can go back and fairly easily review the content. If you're dying for more, the book is out and available, and I'd be happy to stay around and chat with any of you afterwards. I do hope some of this ends up being useful in your own work. Thank you all for being here. It was a pleasure being with you all, and good luck in your future research. Thank you.